Dear Dr. Margulis, following our conversation to the effect, I would like to propose that we initiate an active research program leading to the development of a diagnostic imaging technique using nuclear magnetic resonance, NMR. Clearly, the payoffs are large, but the risk of failure is commensurate. For us to enter this area of research now will be extremely timely. Sincerely, Leon Kaufman.
In 1975, Dr. Leon Kaufman was employed in the Nuclear Radiology Division at the University of California, San Francisco. As a physics student at UC Berkeley in the early 1960s, he learned that a nuclear magnetic resonance signal, or NMR, could be used to create images by localizing its signal in tissue matter. But no one had seen the need to do so. In the 1970s, however, Kaufman recognized potential applications for such a technology. His boss, the chair of the Department of Radiology, was Dr. Alexander Margulis.
In those days, nuclear magnetic resonance was a chemical approach to do chemical analysis. And Kaufman was far-sighted. He felt that this is one way of imaging to also do chemical analysis.
Kaufman had a vision to engineer a machine that would come to be called MRI, a magnetic resonance imaging technology. But he was not the only one.
Other research teams were already making inroads to the development of MRI, notably in New York and in the United Kingdom.
In 1971, Raymond Damadian, a research physician at the State University of New York's Downstate Medical School in Brooklyn, published an article in the journal Science reporting that NMR can be used to differentiate between cancerous and normal tissue. He filed a patent the next year on a full-body cancer scanning apparatus. Paul Lauterbur was a chemist on the faculty at the State University of New York in Stony Brook and was also acting president of a struggling company called NMR Specialties. His 1973 article in the journal Nature contained the first published NMR image, a scan of 2 water-filled test tubes. Meanwhile, in the United Kingdom, Peter Mansfield at the University of Nottingham published the first human image using NMR. It was an image of a human finger. Interest at UCSF came relatively late in the game, yet by 1982, they became the first team to manufacture a machine that would sell to a hospital for clinical use.
While this group's story is set within an international context of research and medical engineering, their particular success captures the spirit of innovation and entrepreneurship that helped lay the foundation for biotechnology's future, but not without doubts and questions.
Yeah, I thought this was a little riskier. More money involved, new technology, breakthrough kind of a product.
That's the jumping off point for the second stage of my career, because I began to ask myself, what is the economics of healthcare? How do you justify this and what we're doing?
Examining the story behind the images of this revolutionary technology, we gain insight to the workings of venture capitalism, university corporate relations, and the values of medical innovation.
Successful enterprises create a lot of animosity and jealousy.
University of California, San Francisco, in the mid-1970s. The School of Medicine was building its future around a culture of basic science research and biotechnology development, enjoying steady increases in external research funding. It was also adjacent to the birthplace of the biotechnology revolution. In 1976, UCSF biochemist Herbert Boyer and venture capitalist Robert Swanson founded Genentech, a genetics engineering technology company headquartered in South San Francisco. University and corporate collaborations, or private-public partnerships, were a new model for scientific research and development. Institutional patent agreements, established in 1968, simplified the process of patenting federally funded university research. Risks incurred in development offered potentially high rewards. Leon Kaufman saw a relevant social context in which to pitch his idea that recognized corporate interests and newfound market possibilities for high-end medical devices. In 1972, computed tomography, or CT scanning, was the first major development in imaging technology since the development of ultrasound in the 1940s. Using X-rays and powerful computer processing capabilities, CT yielded image slices of the human body that differentiated between tissue densities. In CT, X-ray shadows are converted into grayscale pixels on a monitor, each with a numeric value. Computer algorithms reconstruct a cross-section image of the body from thousands of angles. Spurred by low-cost computing capabilities, spawned by Silicon Valley, medical imaging technology saw phenomenal growth in the 1970s, with CT paving the way.
And then CT came. CT is really the inventor of NMR.
Because NMR would also use computers to reconstruct images, the pixelated pictures would look similar to CT scans, yet the way the data was generated was very different. Specific characteristics of the behavior of different nuclei when exposed to a strong magnetic field can provide information on chemical structure and ultimately on human tissue differentiation. Leon Kaufman was convinced of the potential uses and benefits of NMR, not least since this technique did not require radiation exposure, such as X-rays as used in CT. What he needed was institutional support to pursue his vision.
Well, he was very persuasive, and I have heard about several other universities starting programs, and I respected Leon very much. So there was no question. The amount of money that he was asking was not huge.
Everything came together. It was a time of true entrepreneurship at the university, at least at this particular university, without question.
The Department of Radiology provided $40,000, a sum matched by the Dean of UCSF's School of Medicine. Meanwhile, space was allocated for the project in the basement corner of a medical science building.
Now that I had the money, I had to do something, and I had no idea what I was going to do next. I had been a TA for Erwin Hahn when I was in Berkeley. So I went to see Erwin, and he told me flat out, you can't do an image. The wavelength is too long. So he told me, no, you cannot do it. But he sent me to see Jay Singer in electrical engineering, who I did not know. I knocked on Jay Singer's door and I said, Erwin Hahn told me to come and see you. Can we make it, can we make an image with NMR? And he went, oh yeah, that's easy.
In the 1950s, Jerome Singer was building on the pioneering research by Edward Purcell and Felix Bloch, who had won the Nobel Prize for their work in nuclear magnetic resonance in 1952. They were the first to produce calculations of the relaxation time of hydrogen atoms, meaning the time it takes for an electromagnetically excited atom to revert to a stable state when removed from that magnetic field. This energy relaxation, or NMR signal decay, is the basis of what is called T1 and T2 calculations. In an article published in Science magazine in 1959, Singer described how these principles could be used to take measurements of blood flow, and his lab went on to research the uses of NMR as a technique to study blood disorders, particularly leukemia.
So Jay got me one of his students, Tom Grover. He came to work, and we borrowed the magnet from Dave Hollander in nuclear engineering. And we started to do some work. Then we got two more people from Jay's shop, John Honencher and Jeff Watts. Jeff Watts was a programmer, John Honencher an electrical engineer and circuit designer. We started to build equipment and make images.
The team had a small magnet, a computer, and some rats to work on. A larger magnet was on order from Varian Associates in Palo Alto. But assembling the core team immediately proved more of a challenge. Larry Crooks was still finishing his PhD thesis with Jay Singer when he was contacted.
Tom Grover decided that he could not stand to continue to live in San Francisco and work in this sub-basement of the Health Science West Tower that was a solid concrete bunker with no windows to the outside world, and gave his notice, at which point Leon was looking for someone. Our goal was to do what I had been doing with the blood samples, which was excite the nuclei with a very short RF pulse and then watch the signal that comes back from them.
One of the crucial components to the project was the radio frequency coil, or RF coil. One person who happened to be visiting the Bay Area with the potential of securing a job at Varian Associates was Mitsu Arakawa, a radio frequency field engineer at a Japanese company.
And the way we got Mitsu was a well-known and generally recognized as, if not the top, one of the top RF people in the world at JOL, Japan Electro-Optical Laboratories. So I said, okay, tonight at dinner, you say that you mentioned to Leon that you told me about Mitsu, and that I offered him a job for $20,000 a year. So he came back the next morning and says, Leon, I said what you said, and his wife said, yes, you take it. So we got Mitsu, and Mitsu, of course, was key.
At that time, I think I heard about this very old technology using NMR, but I was not a believer of it. So I came along and looked initially quite a bit of disappointed. Ooh, I don't know if this will work because it's just a small magnet and very low field, and the imaging, I think at that time Dr. Crooks mentioned it takes several hours to just kind of get some slice.
We then put an object in, and you could move it one point at a time and up and out, in and out. And we indeed created very crude images that way of an object that was made of plastic and water compartments. You could see the compartments. And then we did a rat through the head, so you could sort of see there was a brain in the skull and in the chest, and there was a bright blob that was the heart in the middle of a dark lung field. And that was our first imaging and publication.
When Larry Crooks showed me the first picture of a rat's heart, I was very disappointed. And they were very excited, and this was somewhat of a puzzle to me.
This was probably their first direct experience of the challenges of translational research, and in particular, getting people to recognize images with this new kind of imaging modality. It's easy to assume that pictures are self-evident, yet these early MRI pictures illustrate that the principles behind the technology needed to be understood before the images themselves could be understood. Figuring out how to produce images was one thing. Explaining what they meant to people from different disciplines was quite another.
If they are so excited, it must be that I'm not seeing it. And in the beginning, the radiology community was very skeptical. I gave several talks at meetings, and when I would start showing the rat images, you would have thought that there was a fire in the room because people were leaving in droves.
By the end of the 1970s, more images were being published in journals, slowly drawing attention to the activities of the different research groups. At an interdisciplinary seminar at UCSF, Larry Crooks made a presentation on their NMR imaging research. It was accompanied by a sheath of papers containing triple integral equations that were off-putting to most people. But one attendee was Bill Bradley, who held a PhD in physics and a medical degree from UCSF.
He knew that I went to Caltech undergrad, so he said something like, "Hey, Caltech hotshot, understand this." And so I went home that night and read it, and it was like, The Godfather Part 1, when he's struck by the thunderbolt. The same thing. I thought, wow, is this cool? My initial involvement was trying to understand how you made images. And, what's T1? What's T2? What factors affect image quality or the contrast you get on an image? That was my initial thing. And then, it's fairly basic by today's standards, but again, there wasn't a single reference you could go to. There were only papers. And there were books, but the books were written by high-end physicists and chemists for other high-end physicists and chemists. So I had to kind of struggle through some of the early literature.
It was one thing to articulate the principles and promises of the technology, but quite another to demonstrate it with good images. At UCSF, the team had worked its way up from imaging rats, comparing the images to anatomical sections cut from frozen specimens, to preparing for the next step, imaging human anatomy.
The physician wanted, and I'm sure Leon wanted some human image, not just a web image. My wife, you just met, put her hand in that, her hand was a little small, so just fit into the wet imager and go inside that small RF cage. About, I think maybe over 30 minutes. She complained later how uncomfortable that was. And she could not move on the small cages and some kind of funny tick noise coming along.
Radiobiology experiments on animal cells had shown that using high magnetic fields to induce reactions in nuclei caused no damage, but the images remained poor. As the UCSF team learned, for good human images to be obtained, a much larger apparatus was required, but that would cost more money. The initial seed funding procured by the Department of Radiology and the Dean's Office was, by 1978, already gone. What the team needed was corporate investment.
And Pfizer at the time was interested to go into imaging. It was exciting. It seemed to be something that will bring money. And Pfizer had CT machines. And they got also infected with a zeal for MR. And they funded, through a friend of Leon Kaufman's, they funded our research.
There was a fellow named Greg Gardner, brilliant guy. I never knew exactly what his title or responsibility was, but he seemed to know the company and have access and so on. We talked, and within I forgot. It didn't take long. Within weeks, we had a $75,000 check to buy our own magnet. We have an NDE, and we had a law firm to start patenting.
The magnet they planned to purchase would be the largest yet, and was necessary for the construction of a human imaging machine. At a couple of tons in weight, this was not a piece of technology easily bought, nor was it easily housed. But the team had now moved out of their basement room in the campus medical science building to a separate facility in South San Francisco, named RIL, Radiologic Imaging Laboratories.
At one of the conferences, I talked to the sales representative of Intermagnetics General in Guilderland, New York, who made superconducting magnets. And I knew slightly about those because Joseph Battacletti, who was a competitor with Jay Singer in the measure blood flow with NMR field, had purchased a 2 Tesla superconducting magnet that had a terrible field uniformity but didn't need very good for the blood flow work. And when we told Greg Gardner about it, he said, a superconducting magnet. It sounds so sexy, every physician will want one. So he was all for it, but Intermagnetics General, the General meant that it was affiliated with General Electric, the competitor in the CT market. So he would not consider them as a supplier. And the next most likely people were Oxford Instruments in England.
Founded in 1959, Oxford Instruments specialized in the manufacture of superconducting technologies and had just arranged to build and supply superconducting magnets for Hammersmith Hospital in London, where a team was developing their own NMR imager. The race for getting the right parts for the technology was now international competition. Obtaining the magnet turned out to be more complicated than they anticipated, and complications with power supply and shielding needed to be overcome. But when it was finally rigged for imaging a human being, they were eager to conduct these experiments on themselves.
But again, there was luck. We didn't realize that you have to totally fill the magnet with a body. And luckily, the first subject in the machine was Leon. And Leon was fat, and he filled the magnet, and we got absolutely superb images. When we got Larry into the magnet, they were lousy because Larry was so much thinner, and there was free air around it.
It was a very eye-opening experience. I could not believe the clarity of the image myself. That's like, wow, this is it.
By late 1981, some 5 years after the first blobs they produced, which originally disappointed Margulis, the images now were remarkably improved. The team amazed the audience when they presented them at an international radiology conference.
The first images were then in 1982 at the Radiologic Society of North America. And people couldn't believe how good they were. And then at that same meeting where we were crowned with success and inebriated and happy, we were told by Pfizer that they are losing so much money on imaging they're getting out.
Pfizer was in the CT market, as I said, competing eventually with the likes of GE, and that business was not anything that the drug company thought was profitable enough, and they got out of the business. And when Leon could see that coming, he was searching for a new partner.
So I contacted Annette Campbell-White, who is a investment venture person, and I contacted Hirsch Handmaker, a physician of the Bay Area that was an entrepreneur on his own. And I said, do you know anybody who can lose $20 million? And interestingly enough, both of them thought of Al Waxman.
Albert Waxman was CEO and president of Diasonics, a company he founded in the late 1960s to manufacture ultrasound diagnostic systems.
And Diasonics had grown rather impressively as a company into the 1980s in that period of time. And as the CEO of the company, I was looking for opportunities and other areas of growth without emulating what others were doing. I mean, I wasn't trying to become an X-ray company or a nuclear medicine company. I was interested in really new technologies and new directions of medical imaging.
Waxman had earned a PhD in solid-state physics and early on had worked at RCA Labs. He was interested in electronics. It was the late 1960s, early 70s, and his opposition to the Vietnam War influenced him to apply his physics knowledge to some sort of medical use rather than war. A friend of his who had established an electronics company came to Waxman with an idea to use silicon technology for mass image storage. At that time, all of the storage technology for digital computer images was magnetic tape, and he thought that you could build mass memory for storage using silicon. So this prompted a transition from physics to an interest in digital imaging that launched Waxman's career. And with the success of Diasonics, he was interested in what Leon Kaufman had to say.
So I visited Leon at the radiation imaging laboratory and at that time, which existed at that time in South San Francisco. And he showed me pictures, of rats. Okay. I had a pretty reasonable understanding of what was happening since I was a physicist and what the potentials for it were. I did, my diligence and had a few other people who helped me in doing diligence on this thing. Spent a lot of time with Leon. Okay, spent some time with Alex, but not a huge amount of time with Alex Margulis. And really became convinced it was an interesting, it was a worthwhile project. It was something that was very worthwhile, worth doing.
To take on the project, Diasonics needed to buy out Pfizer, acquire the patents they had developed on the technologies, and integrate the UCSF RIL team with their own corporate structure. To accomplish this, Waxman needed to raise about $30 million. He needed investment, and so he turned to the venture capitalist who had originally invested in Diasonics and became its first chairman of the board, Arthur Rock.
Arthur Rock received his MBA from Harvard University and quickly found success in investment banking, having a keen eye for applied science stocks in the late 1950s. He's called the father of Silicon Valley, providing the capital investment for companies including Fairchild Semiconductor, Intel, and Apple.
I saw an entrepreneur in Al Waxman, and his ideas sounded very good to me. And then I got Bob Noyce interested, who had some more knowledge of the physics involved.
Bob Noyce was the co-founder of Intel and was someone that Rock trusted to help due diligence for his investments, to examine the plausibility of the proposed endeavor. Arthur Rock is also an investor who is attracted to funding technologies that benefit society, and that made this vision for the future of Diasonics, centered on medical technology, that much more appealing.
It seemed like an awfully big deal. And Al was just certain he could do it, and Noyce thought the physics was there. So we said, let's have a go at it.
Diasonics was based in Milpitas, California, near San Jose, but they set up a plant in South San Francisco, next to RIL. By 1982, with all the new people in place, they moved full throttle to get a clinically useful machine built and to apply for FDA approval.
So we picked up funding from them, and in the early years, our vision was we were the advanced engineering team for them. We did the designs, integrated the systems, and got them programmed and up and running, and expected them to try to take those designs and manufacture them.
It took years of tweaking to produce a good image with reduced fuzzy noise and artifact in the image. But once the parts were in place and Diasonics on board, manufacturing a machine that they could sell took only 1 year. Finding a buyer was a different matter, but it helped that Bill Bradley, who was their clinical fellow during his medical residency, was in the market.
My first job out of residency was at San Jose Hospital, so I was still in the area. And part of the reason I did that was Diasonics was very close to San Jose in Milpitas. And I'd been talking to Al Waxman and Joel Blank and all of those guys, and I thought, hey, if I'm just next to the factory, I'm going to get one of the first MR scanners, which is what I really, really wanted. So at that point, I'd been in touch with my former colleagues and professors at Caltech, and one thing led to another, and I ended up moving to Pasadena. Huntington Medical Research Institute's had a close relationship with Caltech. It still does.
NMR imaging was still experimental. No hospital had yet purchased one for clinical use, and despite the success of CT scanning, which cost about $500,000 for the machine, it was not clear whether hospital administrators would pay $1 million or $1.5 million for this new technology.
We had a series of 3 papers, and I wrote an editorial that said that this is the future of imaging, and that it still is somewhat primitive, but it shows all the signs that will eventually take over. And the journal just said that I was dreaming. This is a ridiculously optimistic view.
Alex can be 5 steps ahead of you before you know it, what you're going to say. Alex saw it. And it was an interesting thing because there were a number of people, both inside the department and outside, well known, that thought he had lost it.
I heard, kind of the "why do we need it" kind of, aren't the tools we have good enough thing. I did not hear people saying, "Oh, this will never work."
Well, the universities are interested in getting money to further their research and to further the hospitals or whatever. Venture capitalists are interested in getting money to return to their investors.
In addition to the cost of the machine, the purchase would involve major hospital construction to shield it magnetically and electronically. This raised further questions about the value of new medical technology. The ethics of bioentrepreneurship involved reconciling a historic tension between economic value to the investment company and medical value to society. A singular event in 1982 helped to clarify certain interests. The wife of a wealthy donor to the Huntington Medical Research Institute was suffering from seizures, and a special visit to RAL in San Francisco was arranged to see if an NMR scan would help for diagnosis. The images showed metastatic disease, which was later confirmed to be metastasis from breast cancer. While the patient's identity was concealed, those images impacted the hospital's ability to raise the money to buy their first scanner.
GE wasn't going to have their first magnets out until the mid-'80s. And actually one of the guys that donated $1 million to us was a GE director. He was on the board of directors, Jim Boswell. And he said, yeah, I'd prefer you get GE, but if they don't have a magnet yet and you want to get into it sooner, go for it. From the time we ordered it until we got it, installed it, was, I think it came in March of '82, and our first clinical images were May 12th, 1982. I can remember that date better than I can remember the birthdays of my 4 kids. The big day.
This suite is located on the 3rd floor here at UCSF's Moffitt Long Hospital. It's a fairly small room. It's cantilevered above a parking lot on heavy steel girders. There's a cardiac operating room above, so we had to shield the ceiling. This Diasonics MTS system is fully functional, and the hospital did not have to build a new facility.
Diasonics had applied for, but would not receive FDA approval for the sale of their NMR imaging systems until spring of 1984.
Prior to getting FDA approval, we had already begun the manufacturing of a few units and the tentative sale of units. We were not really legally able to sell, but it was always a debate. Could you legally sell and recoup your expenses, okay, or could you not? And the rules were very unclear because I think we were the first pre-market approval FDA medical imaging device that had ever occurred. All of them had all been under 510K.
510K refers to an FDA clearance requiring a device manufacturer to file an intent to sell a product that they claim is equivalent to another device already on the market. There was nothing equivalent to NMR imaging, however, but Diasonics interpreted the pre-market approval laws liberally to base their ability to sell upon establishing it was safe and efficacious. It was a tactic that got them into the marketplace first. This engendered further debate about what clinical uses the machine had. There were those who said it was too slow for imaging the whole body, or for organs like the heart, which moved and would therefore cause motion blur. Therefore, early debates focused on neuroradiology, or imaging the brain for diseases that other modalities like CT scan couldn't pick up. So Diasonics began producing corporate videos using testimonials from physicians to underscore these applications.
A recent case imaged with both NMR and CT illustrates this fact. A woman imaged with CT was shown to have a suggestion of a slightly hyperdense extraaxial collection on the left side. No definite pathology was identified on the right side. NMR imaging performed 2 hours after the CT scan dramatically shows the presence of bilateral subdural hematomas, thus illustrating the superior sensitivity of NMR to the depiction of pathologic changes in the brain.
We never thought MRI would go beyond the brain, imaging the brain. And gradually people found other uses for it. So it became a much bigger deal than we had originally thought.
Having gotten in early, Diasonics managed to seize control of 20% of the market in the mid-1980s. One major competitor was General Electric, who aggressively entered the MRI imaging business and was eating up market share.
There was not an unreasonable amount of rivalry between GE and Diasonics, even though Diasonics was a very little company. And they used every conceivable way to convince the market that they were right. And they did. They did convince the market they were right. They weren't right, but they convinced the market they were right.
Well, after we proved that it could be done and sold, then we started getting competition. And problems developed very early in that these machines sold for $1.5 million or so dollars. And Diasonics was a small company and needed to get that money immediately. 30 days is normal kind of business deal. And General Electric and Siemens, who had lots of money, they had lots of cash, came in to the hospitals and said, look, we'll put this machine in here and try it for a year. And then after a year, if you don't like it, we'll take it back. If you like it, you can pay us. And we couldn't stand that.
Resources to be able to come in.
Finance it, muscled right in. And if I were them, I would have done the same thing.
Throughout the 1980s, the MRI market saw increased competition. Despite further technological innovations in image acquisition and processing, Diasonics suffered setbacks with shareholder lawsuits and patent disputes. In 1989, the Toshiba Corporation acquired Diasonics' MRI division for $187 million and became a licensee of its patents.
You kind of look at what happens to young medical imaging companies like Diasonics. They succeed, and then they get sold. And if they're fortunate, as we were, they get sold for good prices.
I think this story is great because it shows how a new technology goes from a concept and through this translational interaction with scientists and clinicians to something that's very, very useful. I think that for non-emergent imaging, where CT is still very, very good, for non-emergent imaging, MRI is the dominant imaging modality on the planet.
To me, the indication that MRI had made it was the day I was walking along the hallways at Long Hospital, and there were some signs in there, and one pointed to the bathroom, and the bathrooms and the other one pointed to the MRI. You know, it became that common that you don't have to have neon lights saying this way to MRI.
The vision of the Diasonics MTS team is now a reality. We think Dr. Alexander Margulis summed it up best.
Probably the most significant development in imaging since the introduction of X-rays at the turn of the 19th century.
From the original idea in 1975, through the creation of corporate partnerships to the sale of Diasonics MRI in 1989, the research team from San Francisco had designed and built a new imaging modality, placed it in a California hospital before anybody else, and demonstrated how the entrepreneurial spirit works. It was the beginning of a biomedical research culture that shapes modern medical research today.